Hello and welcome back to another QUT game design and implementation video. The topic of this video is something a little bit more complex and less to do with Unity or C# directly, but still an important area, some would even say the most important area, to do with making games. The reason for this is that the underlying structure of what we call a shader gives insight into the working of your average game engine, and the programming languages used to write them is what we use to write game engines with directly. Writing shaders is becoming progressively easier as time goes on, but it is still useful to understand the structure of them in an engine like Unity. So first of all, what is a shader? Shaders, at least in Unity, are the frontline aesthetic content that players experience when interacting with a game world, that being how the game content looks. This includes things such as lighting, shading, shadows, scrolling textures, normal maps, general smoothing, billboards, some mesh distortions, and even particle effects. Shaders are typically partnered with what we call materials, changing the way they are rendered on screen using shader-specific languages to manipulate both the vertices and pixels of geometry. The shader pipeline for your average game engine is something constantly evolving alongside rendering technology, but the one within Unity is pretty typical and straightforward. Shaders can be written for game engines in languages specific to computer graphics to communicate with the DirectX or OpenGL Core Graphics API. This usually follows a specific pipeline or sequence of events involving vertices and then pixels to eventually rasterize on your computer screen. Often, the direction of light sources and the game's camera perspective are taken into consideration as some effects are specific to their location. Basically everything you see in a modern-day game is influenced by a shader in some way, as everything passes through some form of shader before being drawn to screen space. They are actually a pretty big deal. In this video, we are covering what is known as Shaderlab and not Shadergraph. Shadergraph is a new, visually driven API in Unity, allowing you to construct shaders in a more straightforward, connect the dots manner. It's good, it works, but it doesn't expose what is really happening within the body of a shader. Shaderlab, however, involves a more traditional way of writing a shader, which is what we will explore today. Additionally, Shadergraph currently requires the use of a new pipeline called the Lightweight Render Pipeline, specific to Unity 2018.1 or higher. You are currently not able to swap between rendering pipelines and shaders without expecting some kind of conflict, particularly regarding light sources. The standard Unity pipeline actually allows unlimited lights and multiple shader passes, which the LRP currently does not. This will probably change in due time, however. Finally, Shaderlab, its setup and relevant CG language usage is what will likely remain the focus of any units relevant to actually writing shaders at QUT will be, at least in the foreseeable future. Therefore, learning how to write shaders in Shaderlab is much more beneficial. Creating a shader in Unity is actually very simple. In your existing or new 3D project, right-click on the Assets folder in your Project window and go to Create, Shader, selecting one of the pre-made shader templates. Unlike C# scripts, the naming conventions of shaders and the shader header in the script are not linked, so call it whatever you want. Open this shader up in your editor of choice and have a quick look over what it entails. You may not understand a drop of it at this point, but it does highlight how a shader should look. When you are done, select the entire shader's contents and delete it. We are starting from scratch. To start off with our shader, let's begin with the somewhat unofficial but necessary Unity Shaderlab template. Set up or copy and paste the following into your shader script. As you can see, your typical Unity shader has a few very specific declaration blocks that will contain scripting of different types. This is the generic structure of every shader you will write while using Shaderlab in Unity. Feel free to make a backup of this template and rename the header to something more useful. To explain how this shader works, let's first explore, then write up our shader using some basic shader-specific script. Just underneath the overarching shader declaration is what we call properties. Properties are typically variables associated with the shader that you may wish to adjust through Unity or through scripting. These variables are declared within the properties logic block and are manipulated further within the shader. However, they are manipulated using computer graphics code, so they are declared again but refer to these same properties later on. We will come back to this concept very soon. Subshaders are also contained alongside properties within the shader. However, subshaders are where the magic actually occurs, potentially containing multiple rendering passes to manipulate the material in question to look a certain way. Multiple subshaders can be within a single shader if different rendering techniques are required, typically if different hardware needs to be used or is unavailable. Passes are contained within subshaders. Passes typically contain the main guts of a shader, that being the computer graphics language necessary to make vertices and pixels look different. Passes can contain both CG and HLSL code in Unity, and are typically declared between logic blocks starting with CG program and ending with end CG. It is within this block that properties must be redeclared as a different CG-specific type within each pass, but as the same name as the properties in question. With the body of the shader template out of the way, let's utilize it by writing a very simple shader. All this shader will do is color an object red diffuse, but also play around with some of the property types. Let's start by first of all introducing the kinds of properties you may wish to use in your shader. The following block, located directly within the properties declaration, will expose to Unity and your scripts the following types of variables. They are named and are used as you would imagine, though some such as vector4 have some interesting properties. Notice that these properties are declared in a very similar fashion. The name you give them in script, example myTexture, will be that you will link to within your subshader code. The name you give said property in quotations, example myTexture, is what you will see within Unity's inspector view. The property type is also important as this will determine both the default values you can give the property as well as what you can assign it to later within Unity. If you head back into Unity, you will notice your shader will look like the following when attached to a material. However, to access these properties within the subshader, we will need to initialize and link to them using standard computer graphics variable declarations. To do this, add the following to your subshader logic block within the initial pass. This will give you access to the property of the same name when you manipulate them within the workings of a subshader pass. Make note of the naming conventions for the variable types and how they are not the same as what we use for property types. Additionally, note that the name of the variable is the exact same name we have given to the property. We will finish off this video by introducing you to the vertex and fragment component, writing a shader that simply applies a color to a material. To start this, we need to first tell the compiler where our computer graphics code begins and ends. Within the body of the pass logic block, place the following CG code underneath the variables you just declared. This code gives instruction to Unity or Shaderlab, instructing it on what to do with the various vertices and pixels passed through the rendering pipeline. The code you write between the CG program and NCG statements are in typical CG or HLSL language, including possible extensions into OpenGL. The pragma statements indicate the name and shader types that need to be compiled for our surface, vertex, or fragment shaders. The data we manipulate within the shader types are usually set up as structures containing the custom information necessary for our shaders computation. As an example, let's place the following below the last pragma statement. The first struct contains the positional data to be used within the vertex shader in the form of the second struct to be used for the purposes of our fragment shader. The geometry of our model will first be passed through our vert function, which will be set up as a declaration of the second struct, altering vertices if necessary. These vertices are then passed through our frag function, which will decide the color of our eventual pixel placement. The vertex shader will process the information first and pass the result to the fragment or pixel shader later, so the order is important. Therefore, we can now write the code for the vertex and fragment shader components something like the following. This code is where we declare what occurs in our vertex, i.e. vert, and fragment, i.e. frag, shader functions that we declared for compilation via pragma earlier. Take note of the syntax used here and how we are using our structures to assign input parameters for our vertex and fragment shader components. So, all this shader currently does is use our vert and frag functions to recolor our model's geometric material red. You can test to see if this is working by adding an object such as a capsule to your scene and applying the material to it, like so. This should result in the object with the material applied appearing red diffuse. So that's all for this video. It is likely that I will create an additional 1 or 2 more advanced shader videos in the future, showcasing something like a vertex displacement lava shader or possibly something involving Phong lighting and hard shadows. So stay tuned for more advanced shading videos sometime in the future.